Okay, welcome to the last review video of the year. This is our light and optics unit. And we also have a little bit of atomic physics at the end. So at the beginning of this unit, we think about light as a wave. And when we think about light as a wave, it has a wavelength. So visible light is between 400 nanometers and 700 nanometers. 700 is the longest, so red, and 400 the shortest is violet. Green is in between, about 550 nanometers. Amplitude determines how bright the light is, and light is a transverse wave. Now, one of the big differences between light and sound is not only that light is transverse, but also that light can travel through a vacuum. It does not require a medium. If you remember in the last video, we talked about sound needs a medium. It needs to go through air. Light does not need a medium. It can travel through empty space. Now, visible light belongs to a family of waves, and this family is called the electromagnetic spectrum. And you should know the 7 types of electromagnetic waves. From lowest energy to highest energy. So the radio waves have the lowest energy, gamma waves have the highest energy. Energy is determined by frequency, so they have a low frequency, and gamma waves have a high frequency. All members of this family have the same speed. Same speed, and that speed is the speed of light, 3 times 10 to the 8th meter per second. Okay, go ahead and try this problem. Pause your video now. You should have attempted this problem on your own. It says the length of the most effective transmitting antenna is equal to 1/4 of the wavelength of a broadcast wave. If a radio station has an antenna 4.5 meters long, what is the broadcast frequency? So we're going to be using the wave speed equation. Speed equals wavelength times frequency. And since we're talking about a radio wave, the speed is the speed of light. And we are looking for the frequency, so frequency is the speed of light divided by lambda. And it says that the antenna is 1/4 of the wavelength. So if the antenna is 4.5 meters long, then the wavelength is 4 times 4.5 meters, or 18 meters. So that's what I'm going to use right here, and I know the speed of light. So frequency equals 3 times 10 to the 8th divided by 18. I'm noticing that this is an estimation problem. So if we're estimating here, this is approximately, okay, so I still have 3 times 10 to the 8th. I'm going to round this up to 20, or 2 times 10 to the 1st power. So I just did an estimation. And that 3 divided by 2 is 1.5 times 10 to the 7th. And so this is looking like my answer in hertz. Okay. Now, anytime 2 waves encounter each other, they experience interference. And the most famous example of this for light is called the double slit experiment, Young's double slit experiment. And so we have this equation for the double slit experiment. And we also have an approximation. So this is called the small angle approximation. In these equations, we get bright spots when m is a 0 or an integer number, and we get dark spots when it's a half integer. So let me just show you with this picture. So right here is where you would have your double slit or your single slit or your diffraction grating, and this represents the screen. So for a double slit, you notice we get a bright spot at 0, 1, 2, 3, or 1, 2, 3 on the opposite side. For a diffraction, so that was a double slit. For a diffraction grating, the bright spots occur at the same positions, 0, 1, 2, 3, 1, 2, 3. The difference is with a diffraction grating, we have bright points. So bright points surrounded by darkness. But with a double slit, we have more of a fade in and a fade out. But the bright spots do occur at the same spots. Now with a single slit, you reverse your conditions. So we still have a bright spot at 0, but then the next bright spot doesn't happen until 1.5 and then 2.5. Same thing on the bottom, 1.5 and 2.5. So we reverse our conditions for where it's going to be bright and where it's going to be dark. Also notice for a single slit, the central bright area is wider than the other two. Go ahead and try the next problem. The next two problems, one on this page, one on the next. Pause your video now. Okay, you should have tried this problem and the next one. In Young's double slit experiment, the second order bright band of one light source overlaps the third order band of another light source. If the first light source has a wavelength of 660, what is the wavelength of the second light source? So what's happening here is for the first light, for light number 1, M equals the second order, so M equals 2. And for light number 2, it's the third order band, so M equals 3. Now, what I'm going to do is I'm going to use this approximation, x equals m lambda L, m lambda L over d, yes. I'm going to use this equation, the approximation. And since they're overlapping, that means that the x over here equals the x over here. Okay, but the m's are different. So I can set these equal to each other. So m lambda L over d. Lambda 1 equals m lambda 2L over d. Now we're using the same screen, so L is the same. We're using the same slit, so D is the same. Those cancel. So I end up with just m lambda 1 equals m lambda 2. M is 2 here, and lambda 1 is 660 nanometers. This m is 3, and this lambda is what we're looking for. So I'm plugging this in, and I get an answer of lambda 2 equals 440 nanometers. Now there's other ways to do this problem. What you might have done is, well, actually that's probably the best way to do this problem. Let's keep going. Here's another double slit experiment. The slit separation is doubled. So I'm going to write my equation. X is approximately m lambda L over d. And the two slits, that variable is d. So if d is doubled, to maintain the same fringe spacing, that's x, what has to happen to the distance to the screen? I'm calling that L in my equation. So x equals m lambda if d is doubled to 2d. For this to be the same, I also have to double the length, the distance to the screen. And so the answer here is going to be 2D. The other example of interference you need to know about is thin film interference. This equation, by the way, is not on your equation sheet, so be sure you know that. Little tricks here that you have to remember is, one, the number of phase changes. So there is a phase change every time we reflect off of a slower medium. So if both of the reflections have a phase change, you can ignore it completely. So that's here. But if you only have one phase change, then you have to switch your M's for constructive and destructive. The other little detail that you need to remember is that in this equation, make sure you use lambda inside the film. Don't use lambda in the air. Okay, try this thin film problem. Pause your video now. You should have attempted this problem. A light ray is incident, normal to a thin layer of glass. Given the figure, what is the minimum thickness of the glass that gives the reflected light an orangish color? Okay, so we're going to use our 2t equals m lambda equation. 2t is called the path difference. Here, since it said minimum thickness, I'm either going to be using m equals 1 or m equals 0.5. I'm going to count the phase changes. Going from air to glass, I have a phase change because the light is slowing down when it bounces off the glass. But down when it hits the water, it speeds up, so I don't have a phase change. So since I only have one phase change, and we're looking for reflected light, that's constructive interference, I'm going to use m equals 0.5. So 2t equals 0.5 times the wavelength. Now I have to use the wavelength in the film, and the way that I do that is I find the wavelength, so 600 times 10 to the negative 9. I take the wavelength in the air and I divide by the index, 1.5. So this is going to give us t equals 0.25 times 400 nanometers. So the thickness is 100 nanometers. Okay, at this point in the unit, we're no longer thinking about light as a wave. Now we're thinking about it as a ray, a straight line ray. Trying to answer this question about a plane mirror, pause your video now. Okay, anytime we have a plane mirror, the image is virtual. It has the same orientation, size, and distance as the object. So the only one that shows me that is number 3. Here's the object, here's the image. They have the same size, same orientation, they're both pointing up, and same distance. Refraction occurs when light travels from one medium to a different medium. The speed changes, and so the direction changes as well. You see the direction here. Now, if this is the boundary, we always have to draw a normal line that's perpendicular to the boundary. And we're looking at the angles that the light makes with the normal line. So here, since this angle is bigger, the light is traveling faster here and slower here. Bigger the angle from the normal, faster the speed. If it's moving faster, it has a smaller index, n. If it's moving slower, it has a larger index, n. Snell's law tells us exactly what angle the light will be refracted to, given the two indexes. Go ahead and try the next problem on your own. Pause your video now. Okay, you should have tried this refraction problem. Diagram below shows the path taken by monochromatic, that means single color light, as it passes through three media. We want to know which is true. So first of all, you have to draw your normal lines. I can't tell you how many people forget to draw their normal lines. So I draw a perpendicular line at every boundary. Look at the angles that the light makes with your normal line. The bigger the angle, the faster the speed. So down here, we're moving the fastest because it has the biggest angle. In medium 2, we're moving the slowest because it has the smallest angle. So the first thing that I'll look at on the answer choices is the speeds. V3 is the fastest. So B cannot be true because V1 is not the fastest. D cannot be true because V2 is not the fastest. Okay, so now I have to start looking at wavelength and frequency. So one thing that I hope you remember is that when light goes from one medium to the next, the frequency never changes. So the frequency can't be greater for any of them. So I'm comparing the wavelength. Wavelength equals speed over frequency. Frequency is the same for all of them, so the one with the fastest speed will have the greatest wavelength. That's medium 3. So it should be medium 3 is the biggest, medium 2 is the smallest. Choice E. Okay, we learned our three rules for ray diagrams. Rule 1, the first ray comes in parallel and it reflects through the focus. Here's the focus right here. Rule 2, it comes in through the focus, it reflects parallel to the principal axis. Rule number 3, going through the center of curvature and back through the center of curvature. We draw the image where the three rays meet. So take a minute here, pause the video, take a look at these diagrams, read through these points, take a minute, pause the video now. Okay, you should have looked through all those diagrams. Now we have 4 questions. If you have not answered these questions, pause your video, answer the questions now. Okay, you should have tried all 4 of these questions. Here we have a convex lens. This is a convex lens. And we're first looking for which ray represents the path of ray A after it emerges from the lens. So ray A travels parallel. When it hits the lens, it will be refracted through the focus. That's rule number 1 for ray diagrams. So that would be path 3. The image of the object formed by the lens is, so first is it real or virtual? Anytime your object is behind the focus, we get a real image, so it cannot be virtual. Is it going to be erect, meaning upright, or inverted, meaning upside down? Real images are always inverted. So choice 4. How far from the lens is the image formed? For this, we want to use our equation. If I do, I die. 1 over F equals 1 over DO plus 1 over DI. And we're looking for how far is the image formed, so I'm looking for DI. Okay, so 1 over DI equals 1 over the focus, which is 1 over 8 centimeters, minus 1 over distance of object, 1 over 10. 1/8 minus 1/10, 1 over di equals 0.025. And then when I take the reciprocal of that, I get 40 centimeters. Which phenomena best explains why the lens produces an image? That would be refraction. We have a new medium. It was air, now it's glass. And when we have a new medium, we have a change in speed. We also have a change in direction. That's what refraction means. Okay. After we studied the behavior of light, we started to ask ourselves, where does light come from? And what we learned is that light comes from atoms when electrons fall down from an excited state to a lower state. When an electron falls down to a lower energy level, it releases a photon, and that's a packet of light. Okay, please pause your video, take a minute, pause your video, read through these points for the energy levels and photons. Okay, you should have read through all these points. Also, you want to try these questions on your own first. So if you haven't tried these, pause your video now. Okay, by now, you should have read through all these points. You should have tried both of these problems. Let's go through them together. The diagram shows the lowest 4 energy levels for an atom. The electron is excited to the -1 state. Okay, here's our electron up here. It transitions to the lowest energy state by emitting only 2 photons. Which of the following energies could not belong to either of the photons? Okay, so if it emits 2 photons, it means it went down to the lowest level in steps. 2 steps. Could have gone 1, 2 like this, or it could have gone 1, 2 like this. Look at the energy difference. 1 to 3, that would be 2 electron volts. 3 to 12, that would be 9 electron volts. 1 to 7, that would be 6 electron volts. And 7 to 12, that would be 5 electron volts. So can't be 2, that's possible. Can't be 5, can't be 6, can't be 9, those are all possible. The only one that couldn't be emitted is a 4 electron volt photon. Which of the following transitions will produce the photon with the longest wavelength? So think about your equation E equals hc over lambda. So lambda equals hc over E. hc is a constant, that doesn't change. So if I want the longest wavelength possible, if I want a really big wavelength, I want to be dividing by a really small energy. Which of these has the smallest energy? 2 to 1, that's an energy of 3 eV. 3 to 1, that's an energy of 5 eV. 3 to 2, that's an energy of 2 eV. 4 to 1, I'm going to ignore that, that's the biggest one here. Or 4 to 3, that's an energy of 1 eV. Okay, the smallest energy possible is going from 4 to 3. That's only 1 electron volt. So that would give us a photon of 1 eV. Okay, very end of the unit, we spent 1 day on nuclear decay. Now when we talk about nuclear decay, we're talking about what's happening in the nucleus of an atom. So don't confuse nuclear decay with energy levels. This is what's happening outside the nucleus, in the electron cloud. Nuclear decay deals strictly with what's happening inside the nucleus. So there's 3 types of nuclear decay. Alpha decay first. In alpha decay, the nucleus emits a helium atom. So that means 2 protons, 2 neutrons. Helium, so 2 protons, it has an atomic number of 2, and it has a mass of 4, because 2 plus 2 gives us 4. When you have alpha decay, you lose mass in your original atom because the mass goes into the helium atom. In beta decay, an electron is emitted from the nucleus, and when that happens, a neutron turns into a proton, so that charge is conserved. Beta plus decay, a positron is emitted from the nucleus, and a proton turns into a neutron, again, so charge is conserved. And in gamma decay, we're just emitting a high energy, you can think of it like a light wave, but a very high energy light wave, electromagnetic wave. Try these 2 problems, pause your video now. Okay, you should have tried these 2 decay problems. Here we have this nuclear equation. We want to know what is the question mark in the equation. So we have, this is hydrogen. It's an isotope of hydrogen. It has 1 proton and 1 neutron, giving it a total mass of 2. Here's another hydrogen isotope. It's turning into a helium atom that has 2 protons, but since the mass is 3 and the original mass was 4, that must mean that this has to be a neutron. So, got to be a neutron. Okay, this wasn't really a decay problem. It was more of a balancing equation. During a particular kind of decay, a particle is emitted from the nucleus of an atom, and the atom's atomic number increases by 1. That means the number of protons increased. This decay involves the emission of what? So the only type of decay where we get more protons is beta minus. And that's when a neutron turns into a proton. By the way, remember that beta decay just means an electron. Okay? So we must have emitted an electron, which is a beta particle. An electron.